Hey guys, okay, so today we're going to be doing a very small chapter, and this is a very easy to one to get. It's called Group 2, and we'll be studying about the elements of Group 2 and their trends. We'll start off with magnesium and going all the way down to barium. We won't be studying beryllium, which is in period 2, generally because period 2 elements are so small, they are not typical of any element in the rest of the group. So beryllium is being ignored mostly in its chemical property, especially because it's really reactive differently. It makes covalent bonds with most molecules, and it doesn't follow the same trends in many properties chemically, which is why we don't study it, because we're studying here trends and understanding how we can apply trends across periods or down groups. Now, this is a good follow from the previous video, because starting off the bat, we'll talk about a couple of physical properties, which is the size of the atoms, how it varies down the group, the size of the ions compared to the size of the atoms, like for example magnesium ion, calcium ion compared to the atoms, and their second and first ionization energies. And the reason why we're going to study second is because both of them together is how they're going to go from metal to, let's say, barium 2 plus ion. The energy required to go from barium to barium 2 plus, which is the ions group 2 atoms make, that energy is the sum of the first and second ionization energy. Now, right off the bat, what you'll realize is that down the group, and I'm not going to talk about the melting and boiling points here, but generally down the group they decrease. Now we won't talk about that. We'll be focusing on first ionization energy. As you go down the group, it decreases. Even the second ionization energy, as you go down the group, decreases. Both decrease because of the same reason we discussed in the previous two videos, which is as you go down the group, even though the nuclear charge increases, the shielding effect increases more and the size increases more. Both of them outweigh the increase in nuclear charge. The reason why I'm mentioning them again is because many group 2 questions will contain parts about trends in ionization energy. It'll also contain trends in sizes of the radii. So let me scroll down and show you some of these atoms first. Now here we have beryllium, magnesium and calcium, the first 3 atoms of group 2. Even though we won't be studying beryllium's reactions, but these properties, these sizes will hold true for them also. Now the red circle here represents the orange circle, half circle represents the size of the atom. Now as you go down the group, the size of the atom increases. So we already know that atomic radius down the group will increase. Now we know and we know why that is the case, because the number of shells increase, which means the repulsion between electrons increases, which outweighs the increase in nuclear charge. And then while the cations, these are the blue are the cation sizes, the cations are clearly smaller than the atoms. And there are 2 reasons why the cations of group 2 are smaller than the atoms. One is that each of the cations has 1 less shell than the atom. The atoms, let's say for example in magnesium, the guy has 3 shells. It's 2, 8 and 2. But the ion is only 2, 8. So the ions have 1 less shell. Secondly, there are fewer electrons in the ions, so there's less repulsion between the electrons. And when there's less repulsion from the same nucleus, the attraction is more and the size is smaller. So that's why the radius of group 2 cations is smaller than the radius of the atom. And we've discussed this in detail in the previous video. I'm just tying it up so that when you do questions for this, it's all there right here. Now, the other thing that we're going to talk about, we talked about in the last video, was also ionization energy. But here is a graph of not just the first ionization energy, but the sum of the first and second. And the reason I'm mentioning this here is because we'll talk about 2 things, the trends and what it results in. Now I'm going to scroll this to the side, sorry. Now if you notice the trend, the ionization energies sum is decreasing down the group. And the reason why it's decreasing is because even though the nuclear charge is increasing, the nuclear charge increases, but it is outweighed by, and this is what you write in the exam, outweighed by the increase in shielding effect, which is because of inner shells, and the increase in atomic radius or atomic size. Now both of these result in the electrons being more loosely held even though there's more nuclear charge, and we discussed this in the previous video also. So down the group, the energy required to lose electrons decreases. What that really means is that reactivity for group 2 metals will increase down the group, because it requires less energy for barium to become an ion than magnesium. So barium is more reactive than magnesium, and we'll see this in the reactions with water. It will be very obvious that this magnesium will be less reactive while barium will be much more reactive, and that's what we're going to talk about now. So as far as the physical properties are concerned, you got to know the atomic radius increases down the group, cations are smaller than the atoms, and ionization energy decreases down the group. And you need to remember the factors. If you don't understand these factors, I suggest watch the previous 2 videos, day 3 and day 4, all over again. Okay, so now we're going to start talking about their chemical properties. Now, the first thing you got to remember is that the way the elements all look, they're all silvery gray in color. And why is that important? Because in most reactions, you've got to talk about they will ask you the observation that you're going to make too. Now, right off the bat, all these metals in group 2 are pretty reactive with oxygen. So if you heat them in air, because air has oxygen, they will burn. In fact, they burn to make oxides. Like magnesium burns in oxygen, that's half O2, to make magnesium oxide. Now, you got to know 3 things: the color of the original metal, the color of the compound it's forming, and in this particular case, the flame color. Now, all group 2 metals, magnesium ho gaya, you got calcium, then barium, strontium. Actually, I'll put strontium also. Strontium and barium. These all react the same way. They react with half mole of oxygen gas, okay, to make an oxide. All of these guys. The difference will be in the flame colors. But all 4 of them, the elements will be silver gray in color. And the oxides they make will be white. Like calcium oxide is also white. Strontium oxide is also white, and barium oxide is also white. And the reason for that is they're not transition elements, so they're not colored. They're actually white. The difference is their flame color. So you got to heat them up, but they catch fire right away, and they have different flame colors. Magnesium burns in a white flame, and I'm gonna write that down now. White flame. And you got to learn these colors. I'm sorry, you do have to. Calcium burns with the red flame. Okay. Now, it might look yellow red in some cases, orange red in some cases, or brick red in some cases. Strontium burns with the crimson red color. Not flavor, sorry. Crimson, also, you can also write red, but it's a different feel of red. And I'll show you these colors right now. While barium burns with a green flame. Okay. These are all flame colors. And you have to learn them. They will ask this. And it's a very beautiful thing that when they burn, especially magnesium. Magnesium burns the fastest, because it has a pretty low melting point. So when it burns, it's a brilliant white flame. Not just white, but it's brilliant white, like you can light things up with it. Okay, so we're going to start off the chemical reaction of group 2 with how they react with oxygen. And generally, any group 2 metal, and if I can use X for that, any group 2 metal will react with oxygen to make an oxide. And all of these metals are silver in color, and the oxide will be white in color. And all of them will have a different color flame. But before we talk about flame colors, and before I give you individual reactions, I'm going to show you actually the color of these metals. The reason why it matters is because for all these reactions, you will have to talk about the observation. For example, here, generic observation for all group 2 metals will be that a silvery gray metal burns in oxygen with a different flame color. If you're heating it up to burn in air or oxygen, with a different flame color to form the oxide. And the oxide is a white solid. So the gray metal forms a white solid. I'm going to show you pictures of the gray metals of all the 4: magnesium, calcium, strontium, and barium. And then a video for burning magnesium. So let me just scroll down to show you the pictures of magnesium, calcium, strontium, and barium. Okay, so here I'm showing you the 4 metals of group 2. Look, if you notice, they're all in the similar colors, silvery gray. Now, this is just to get you guys to see they're all similar. Maybe different structures, but they all have the same color. So now when you heat these guys in oxygen, for example, magnesium. Magnesium is a gray solid, reacts with oxygen gas to produce magnesium oxide, which is a white solid. And all of these, magnesium ho gaya, calcium, and strontium and barium all make the oxides. Now I'm going to write the equations down. They all burn in oxygen to form oxides. All have the same color. You would say gray metal, and let's say gray metal burns in oxygen, and all four of them have a different flame color, but they all make a white solid. Now I'll actually show you a video of magnesium burning so you see how it is, and show the flame colors for the other guys. Now what are the flame colors? Magnesium burns in brilliant white, like very bright brilliant white, not a faded anything, but very bright white. Calcium burns in red. Now the red can be orange red or brick red. Strontium burns in also red, but it's called crimson. Now crimson red is slightly different. It's more on the, I'll just show you the color so you can see the difference. And barium burns the green flame. Now you won't have to draw them by color, you just have to learn them by name, because they will ask, well, what flame color does magnesium burn in oxygen? White. Calcium, red. Strontium, crimson or red. This is what they're looking for in the answers, by the way. In MCQs, this is the option they've given, but they're the same thing. And barium burns in a green flame. So now I'm going to show you the flame colors for at least these three, and then the video of magnesium burning. Now it doesn't mean that they only react to form an oxide with air on burning. Over time, as you go down the group, this is more reactive, this is easily burned. But the flame colors are only observed when you are heating it directly under a flame. So they burn intensively to give a different color flame. So I'm going to show you flame colors right now. Scrolling down. So here we have the colors for 3 of the 4. Now the leftmost is for calcium. That's calcium burning in oxygen. The middle one is strontium, and the last one is barium. And these are both considered red. This is orange red, and in different concentrations, it might even be darker red. This is crimson red, so like a little tinge of pink in the red. And this is green for barium. But for the exam, you can learn these both as red for calcium and strontium, and green for barium. And for magnesium, it is white. Now I want to show you a video which is just not even the full video. It's a small part of the video where they're trying to burn some strips of magnesium inside a funny looking face taken from another app, and it burns, and you can see the whiteness, the brilliant whiteness that comes out of it. So I'll just scroll down to show you that. Okay, so scrolling down to this video. So here I'm going to show you magnesium burning in oxygen. So this is dry ice, just to show you that, and you're going to stuff it with magnesium ribbons and light it on fire, and you'll see this burn brilliantly white. So you can see stuffing them and see that burning. Yeah. Okay. I think something wrong with the video completely. There you go. So burning with oxygen. And this is burning oxygen, but the flame is completely white, and this is the white color of magnesium. So anyways, so the idea was that when magnesium burns in air, it burns in a white flame. Calcium burns in a red flame. Strontium burns in a red flame, and barium burns in a green flame. This is flame colors when they burn. Okay, so the next slide we'll talk about how these metals now react with water, but this was metals reacting with oxygen. Okay, so the second thing is group 2 elements reactions with water. All group 2 elements react with water to make the hydroxide and hydrogen gas. Now the only difference is that the rate at which they react. First we'll start off with the reactions with cold water. Now when I say cold water, I mean just room temperature water, not freezing water. Now magnesium metal, that's silver gray, when you add it to cold water, H2O liquid, it starts reacting very slowly, and eventually it makes a slightly alkaline solution, magnesium hydroxide, because there's not enough reaction happening, and that too very slow. And you'll see bubbles of hydrogen gas. The problem is these bubbles will be evolving very slowly. Now compared to the other group 2 elements, now the guy just below it, calcium, reacts much faster, and so the reaction will be the same. They will both make a hydroxide, calcium's solution will be more alkaline because it's reacting more, and we'll discuss later that even the hydroxide is more soluble than magnesium. And it also makes hydrogen gas, just that now the bubbles will be even more rapid. And strontium more vigorously, and then barium the most. So barium's reaction is the most vigorous of all the four. Now, it's not as vigorous as group 1 reactions, because if you remember, group 1 metals react with water very explosively, and they also make a hydroxide and hydrogen gas. But group 2s are much slower, and the reason why the reactivity increases is because you've done this already. Down the group, the ionization energies decrease, therefore the reactivity increases, and that's why barium reacts the fastest. So in the exam, what you're going to get is you're going to be able to ask to write the equations, define what's happening. So silver gray metal dissolves, colorless solution forms, and bubbles of hydrogen gas seen. They'll even ask you to compare the two, or at least magnesium with calcium or magnesium with barium, because that's where the comparison lies. Magnesium may the evolution of bubbles will be very slow, and strontium will be more rapid, barium most rapid. And because we'll do the solubilities also in a bit, but down the group the hydroxides become more soluble, therefore even the pH increases mostly. So this will have the lowest pH or the least alkaline pH, and this will have the most alkaline pH. So you got to remember that this will give you somewhere above 13, 14. Calcium is about 12 point something. Magnesium not so much, because it doesn't dissolve too much anyways. So you need to know the observations. Gray metal dissolves, colorless solution forms, bubbles of hydrogen gas. Bubbles are more rapid as the metals are descended on the group. So barium will be the most rapid evolution of hydrogen gas. All right, so you got to remember that also. So on the next slide, we will talk about the solubilities of both group 2 hydroxides and group 2 sulfates. Now, here we're going to discuss the solubilities of the sulfates and the hydroxides. Let's talk about the hydroxides first. So the hydroxides first, let's talk about them. And then, उसमें क्या है कि magnesium hydroxide is the least soluble in water amongst the whole list. Then you got the calcium hydroxide, solubility increases, and then as you scroll down, you got strontium hydroxide, and the most soluble will be barium hydroxide. Now, and what will happen is as you go down this group, solubility increases, and barium is the most soluble of them all. Of the hydroxides, not the sulfates, we'll get to the sulfates later. Solubility increases. Now what that means is that eventually you are going to make barium hydroxide. When you add that to water, the pH will go down to about 13 to 14. Okay, but these guys will be about 11, 12, and then you go down to 13, 14. So just like how down the group the hydroxides of group 2 increase in the solubility, the opposite happens for the sulfates, which is that down this group the sulfates become less soluble, and you got magnesium sulfate, calcium, strontium, and barium. Now I'm not going to write strontium because it's just a trend. Down the group the solubility decreases, so much so that actually a test for sulfate ions is to add barium ions, because barium aqueous ions, when they are mixed with sulfate aqueous ions from any solution, they both combine to make a precipitate of barium sulfate solid, and it's a white solid. And you can use barium to test for sulfate ions this way, or sulfate ions to test for barium, like in the lab. And because barium sulfate is extremely insoluble, so whenever these two ions from different solutions are mixed together, they will react like this to form barium sulfate. And not so for magnesium, because that's soluble, but down the group the solubility decreases so much that barium sulfate is considered to be insoluble. All right, now obviously the reasons why this happens is studied in second year chemistry, not right now, but in first years all you gotta know is that the group 1 2 sulfates decrease in the solubility down the group, and the group 2 hydroxides increase in solubility. So yeah, that's what you gotta remember. Then we move on to the thermal decomposition of group 2 compounds, 2 sets of compounds. On to the next slide. Okay, so here we're going to discuss the thermal decomposition of group 2 carbonates and nitrates. We'll start off with the carbonates first. And all group 2 carbonates, for example, starting from magnesium carbonate, if you heat them, they will become the oxide and give off carbon dioxide. Now, the same will happen with calcium, and calcium will become calcium oxide, strontium the same, and all the way down to barium. I'm not skipping strontium for any reason, but just so that I don't have to write 4 of them. But all of them do this, and you'll go from the solid state to a solid state, and carbon dioxide will be a gas. The problem is here you see no visible change because the carbonates will be white solid, the oxides will be white solid, and you will never see bubbles. And I have to say that explicitly because people don't realize that you can't see the bubbles of gas because there's no liquid present. It's all solids. So yeah, now this is an important reaction because at times you can heat the carbonates to make the oxides. Yeah, but what you need to remember is that the heat required as you go down the group, the heat required to carry this out will increase. And the reason why it increases, so as you go down the group, and I'll make this line, the temperature delta T for decomposition will increase. What that means is that thermal stability increases down the group of these guys. The more energy needed to decompose them. Now, please don't confuse this with reactivity. That's some reactivities of elements. This is our already carbonates. Now, what happens is when you heat them, they become oxides and carbon dioxides, oxides and carbon dioxides, oxides and carbon dioxides. But their thermal stability is going to increase. Now, why it increases is again part of second year syllabus, not first year. But what it means to be increasing is that the temperature required to decompose these guys will increase down the group. For example, if it requires about 500 degrees to decompose magnesium, it'll require about 900 or 1000 plus to decompose barium. Now, you don't have to learn the temperatures, but I'll show them to you in each. I'll scroll down to show you the temperatures. Just zoom out so we can see all of it. So here the idea is that these are the temperatures required to decomposing these carbonates, and you can clearly see the temperatures are increasing. And so what you need to remember is that it is very easy to decompose magnesium carbonate relative to the others, which could mean that, I mean, in the lab, this could be, you could carry this out using a Bunsen flame. But the Bunsen flame doesn't have enough temperature to decompose the rest of the guys. So if this guy can decompose using Bunsen flames, you need a much stronger heat to decompose the guys below magnesium. And as trends, you need to understand that thermal decomposition, thermal stability increases. So the temperature required to decompose will be greater. Now, and there's no physical observation here. The only way to know this is happening is to collect the gas being produced and pass the gas through lime water. Because if you know, carbon dioxide passed through lime water makes calcium carbonate. And that's something that you should remember from lab theory. So I'm going to pass that. So test for carbon dioxide we can do right now also. Because carbon dioxide passed through lime water, calcium hydroxide makes calcium carbonate and gives me water. And when you do that, that's the milky white that you call it, because it's making a white PPT of calcium carbonate. So scrolling back up, what's happening is this, when you heat the carbonates, they become oxides and carbon dioxides. The temperature of decomposition increases because thermal stability increases. And the only way to test out what's happening is to pass the gas through lime water, which is calcium hydroxide. And the lime water turns white from colorless because it's forming calcium carbonate. And that's a good test for carbon dioxide. Now the same thing, similar trend is existing for the thermal decomposition of group 2 nitrates. Now let's talk about what they are first. So nitrates first. Now, so group 2 nitrates, when you heat them, let's say you got magnesium nitrate. It's NO3 twice because Mg is 2 plus. When you heat this fella, it makes again magnesium oxide, the white solid. And this is also white solid again. Solid compounds of group 2 will always be white because they are colorless. They're not transition elements. But what it also forms is that it forms 2 gases, not 1. Unlike carbonates, it only makes carbon dioxide. Nitrates makes, for each mole of the nitrate compound, it makes 2 moles of NO2 and half a mole of O2. That's the mole ratio. So these both will be gases. Now this one you can see. The reason why you can see this reaction is that this is a brown gas. So when you heat nitrate of group 2, you are going to see some formation of brown gas. And The same for happen with calcium nitrate, magnesium nitrate, and barium nitrate. All of them will make an oxide, 2 moles of NO2 and half a mole of O2. Two different gases instead of just one gas, and NO2 will be a brown gas always. And the same trend applies here, that thermal decomposition increases down the group, which means the temperature required, not delta T, sorry, the temperature required to decompose will increase down the group, because the reasons are done in A2. Just that you have to remember that the thermal decomposition of both carbonates and nitrates for group 2 becomes increasingly difficult down the group. Thermal stability of both of the nitrates and carbonates increases down the group. The temperature required to decompose both nitrates and carbonates increases down the group. But for nitrates, you're going to have two different gases instead of one, and one of those gases will be brown in color, so you will actually see that. So what they can ask you in the exam is write the equation and write an observation. You can't say white solid makes white solid, because that's no change. You got to talk about change here. All right. Now, so these are the reactions done. The last thing left is some uses, and not the uses for all compounds of group 2, just the carbonate and the hydroxide of calcium, because it's a pretty major use in agriculture. So I'm going to move off to that in the next slide. Okay, so here we're going to discuss the uses of calcium carbonate and calcium hydroxide. Calcium carbonate is the main chemical ingredient found in limestone, and limestone was used to make buildings before, and most wooden buildings are still made of limestone now. But nowadays buildings are made of cement, and construction is using cement. But the funny thing is, for cement also you need calcium carbonate, because for cement you need calcium oxide, and they get calcium oxide by heating calcium carbonate to forming calcium oxide, and then the calcium oxide is used to make cement. That's the main uses of calcium carbonate. Now, calcium oxide actually can be converted to calcium hydroxide. In addition to being calcium oxide being used to make cement, you can also use it to make calcium hydroxide by simply adding water. So if you add water to calcium oxide, it becomes calcium hydroxide. And the beauty of calcium hydroxide is it's pretty cheap, and because it's alkaline in nature, it is used to reduce acidity in soils. Simply speaking, calcium hydroxide can neutralize any acid because it's an alkali, and when it does acids, it makes calcium ions and water. And so calcium hydroxide is used by farmers to sprinkle on soils that have acid, because it can neutralize acids, and when it does that, it raises the pH. This guy will raise the pH of soils. If the pH is too acidic, it'll make it less acidic. Okay, anyways, that wraps up for us group 2. See ya tomorrow. Bye.